position embeddings are as patch embeddings to retain positional information. We use standard learnable 1D position embeddings, since we have not observed significant performance gains from using more advanced 2D aware position embeddings. And yeah, I highlighted it because yeah, that was the first doubt in my head, as in I was wondering, why would you, like, I know the priors and the inductive bias comments we had, but I was thinking, like, maybe, just maybe even like you'd add something learnable to, and initialize it with like some weights based on distance from one patch to the other, like how far it is or like which direction, maybe you do at least, at least a few dimensional embedding or something. And they just said, yeah, we thought about it, but it had worse performance. So it was like, okay, that makes sense.
Yeah, I saw that comment that they tried it and it was worse, but they just tried it, like it's only empirical.
Yeah, maybe they
didn't
haven't tried
say
it hard
why.
enough. Yeah. Oh, yeah, maybe maybe we should go and write a paper, try it. So the transformer.
Yeah, I think that aligns good with what they wanted to show, that actually that this transformer doesn't need any 2D aware positioning and less spatial information is better for transformers. So maybe that's because of that.
Yeah, but we can wonder like how far they went in that direction, or like.
Yeah, it's quite convenient because it confirms the theory, right? But they didn't provide any proof, rather than just comment that it was worse.
I guess this will be implicitly learned later, because you have in attention you have every token attends to every other token. So then perhaps if we went deep into analyzing how the attention is distributed among the tokens, right? Maybe there would be some correlation that this patch, patch, say if we have 3x3, patch 4 would have high values when you do 4.1 and like 4.7, right? And 4.5 or something like that. I don't know. I'm speculating here because I've not done that, but maybe it's learned in the layers.
Yes,
also,
but
right?
yeah,
Just, I was thinking of a special case to added like a learnable weights, but those weights, I guess, are in the attention because it's like a graph, right? Attention is like a fully connected graph.
Yes, for the diagrams from below, we actually can see that this one-dimensional positional and embedding is enough, but it's something in the I think in the end of this. No appendix, but closer to the conclusions, I think.
Yeah. Right. Yeah, but that was definitely one of the interesting parts in this paper. Then they have a layer norm applied, so implemented. Yeah. And we have residual connections. Oh, it's yeah. And this MLP just has 2 layers with Jello. Here we have the equation. So the class token prepended, and there's other tokens, and then you got you add positional embedding, and then you go through layers, right? So you do that's multi attention, self attention, right? What's MSA for?
Yes, multi-head self-attention, I think. And it's pretty nice that all of the architecture can be actually put in this only 4 equations, and actually they describe a lot of what is happening there, because
literally this is how to, right? You have a for loop in Python and you implement in PyTorch and you implement it. It would be quite easy, right? Once you have those blocks defined, and then layer norm, and yeah, and that's the strip connection. So there we go. And then you have, they do it. Oh yeah, because they said MLP after they're intertwined, so interleaved. So that's that, right? I guess. And then you have final layer norm.
Yes, we can actually describe this, because maybe it will help somebody to discover what is here. So this Z0 vector first is actually the inputs. So this X class is the class token, as we have spoken before, and every this XP1 vector is actually the patch of some patch of the image that was flattened, and every this E letter is actually the linear layer that is used to map this vector to the dimensionality that these transformers
E stands
access.
for encoder, I guess, right? That's why it's E. Or
Maybe
embedding.
embedding, I think. Yeah, so it's only transferring from this space, this size of space to the dimensionality. And at the end, we are adding for all of this. I think all of this, because it's n+1, so we can answer the Michał question. We are adding this embedding positional embedding to all of these inputs. So also to the X class, because here we have +1, I think.
Yeah, you can
And
say, like you
then
could
we
literally
are
implement it in NumPy, right? Concat or like PyTorch, right? Concat,
yes,
and then you have
the
e
first
plus, and the dimensions agree, right? Times the p squared times c, that's n. This is n+1, but then you have, right, that's e, but e multiplied by that, how many times, and then you have +1 here. So the dimensions agree, and you add it up.
The first step is pretty easy. Then we are just going like L times through the multi self attention and MLP, and in some times we are applying this normalization. But
that's what's
it's
interesting about attention, right? Once you know it and you've heard about it, it's like, yeah, why wasn't it discovered earlier, right?